All right, welcome. In this example, we will take a look at a first order RL circuit, so a resistor inductor circuit. We're told that there's a switch that has been open for a long time, and at time t equals 0, the switch is closed, and the switch is right here. So the question is, what happens in response to this change in the switch condition from open to close? How does the current going through the inductor react? So what's the current to the inductor because of that event? Okay, so in order to do that, let's say that the circuit is, we've been told that the circuit has been around and the switch has been open for a long time. So really the circuit is basically these two resistor and this inductor, but since the circuit has been open for a long time, this inductor is fully charged and acts as a short. So the circuit basically looks like this. Basically it's 75 ohm and a 25 ohm resistor, and that inductor has been replaced here with a short. The current flowing through the inductor is basically the current flowing in this network right now. So with a 100 volt and a 100 ohm current, I'm sorry, 100 ohm resistance, I is V over R, so the initial current flowing here is 1 amp. So this is right before the event, and let's say at t equals 0, the event happens, so the switch is closed, but because the inductor doesn't allow current to change instantaneously, the current at t equals 0 is the same as the current that was before the event. So our initial condition is that the current is 1 amps. Now at t equals 0, the switch is closed. Switch is closed, so the circuit basically looks like this now. So we have a 2 Henry, 25 ohm, and a 75 ohm. And the closed switch, essentially what it does is, since this switch is in parallel to 75 ohms, and the switch has a effective resistance of 0, it's almost as if we placed a 0 ohm resistor in parallel with the 75 ohm resistance, leading us to an effective resistance of this path right here because of this short to be equal to 0. So really that circuit just looks like it has 25 ohms in it. Uh, right, so the total resistance in the circuit is really only 25 ohms. Now, uh, that 25 ohm also happens to be the Thevenin resistance of that circuit. So looking at it from the inductor terminal, so if I look at from these two points point of view of the inductor, the only thing it sees is I zero out the voltage source, and the only resistance it sees is 25 ohms. So the Thevenin resistance is 25 ohms. The reason we're interested in the Thevenin resistance is because the rate of decay or the rate of growth in an inductor current during transient analysis basically depends on this decay factor called tau, which is given by the ratio of L over the Thevenin resistance. So in our case, the Thevenin resistance is 25 ohms, and tau is given as L, which is 2 Henry divided by 25 is equal to 0.08 seconds. So that's our decay or exponential increase factor. Now let's so if we let's wait for a long enough time, that's about 5 tau worth is the lifetime for this. So if we wait a long enough time, the inductor will again fully charge up or discharge and be at steady state and act as a short. So in that case, the circuit would basically look like this. And the inductor current, that's the inductor right here replaced by a short, and the inductor current basically becomes 4 amps. So it's rising or charging up the inductor from 1 amp to 4 amp with this growth rate. So in this case, we have a first order differential equation for the original circuit right here, and the current to the inductor is the solution of that differential equation, and can be written as the current at infinity plus the change in current times the exponential rate at which the current changes. So at long enough time is 4. Initially it was 1, so 1 minus 4 e to the power minus t over 0.08. That's tau. And we are given 4 minus 3 e to the power minus 12.5 t, or you can leave it as 4 minus 3 e to the power minus t divided by 0.08 amps as the current.